the food we eat every day is checked to make sure it is safe and high quality. One of the important fields behind this process is analytical chemistry. Analytical chemistry plays an important role in ensuring food quality and safety. Sugar is widely used in the food industry because it influences both taste and product stability. Because of this, analyzing sugar is necessary to determine its composition, purity, and possible contaminants. To obtain accurate results, advanced analytical techniques such as HPLC, which is known as High Performance Liquid Chromatography, spectroscopy, and mass spectrometry are commonly used. These methods provide detailed and reliable analysis of food components. In addition, analytical methods are useful for detecting adulteration and food fraud, helping to maintain food authenticity and consumer protection. Overall, modern analytical tools enable faster and more reliable quality control processes in the food industry.
So now we will look at the theory part. First, the importance of application of analytical chemistry in food industry is sugar quality analysis. Sugar analysis is carried out to determine the amount of type of sugar present in food and beverage products. Common sugar analyzed include sucrose, glucose, and fructose. This analysis helps ensure the product meet quality requirements and provide accurate nutritional information to consumers. For this analysis, a commonly used method is Fehling method. Fehling method is classical volumetric analytical technique used to determine the presence and concentration of reducing sugar such as glucose and fructose. During this analysis, the sugar solution reacts with Fehling reagent, producing a color change that indicate the presence of reducing sugar. So, Fehling method is important because it is simple, cost-effective, and widely used in food quality control laboratories. It helps manufacturers monitor product quality, maintain consistency between batch, and ensure compliance with food regulation and standard. Therefore, sugar analysis using Fehling method play a significant role in ensure the quality and safety of food products.
Have you ever wondered how food companies ensure that every bottle of orange juice contains a consistent amount of sugar? This consistency is important for product quality and customer satisfaction. To achieve this, analytical chemistry techniques are used to measure sugar content accurately. In this presentation, I will focus on the apparatus used in Fehling methods for sugar analysis. The first apparatus is the pipette. It is used to accurately measure and transfer a fixed volume of Fehling's reagent into the vessels. Accurate measurements are important because they help ensure reliable and consistent analytical results. The second apparatus is the conical flask. These flasks act as the reaction vessels where the sugar, samples, and Fehling reagent are mixed together. Its shapes allow the solution to be swirled easily without spilling, making the experiment safer and more effective. Next, a hot plate or water bath is used to heat the reaction mixture. Heating is an important step because it allows the reaction between the reducing sugar and Fehling reagent to occur properly. During this process, a visible color change can be observed, indicating that the reaction has taken place. Another essential apparatus is the burette. The burette is used during titration to add the sugar solution in a controlled and precise manner. This helps determine the endpoint accurately and improve the precision of the analysis. Together, these apparatus play an important role in ensuring accurate sugar determination. In the food industry, accurate sugar analysis helps maintain product consistency, monitor quality, and ensure compliance with food standards. Therefore, the proper use of this apparatus is essential in the application of analytical chemistry for food quality analysis of sugar.
First is Fehling solution A, which contains copper 2 sulfate. It supplies Cu2 plus ion that react with reducing sugar. During the reaction, these ions are reduced to form a brick red cuprous oxide precipitate, indicating the presence of reducing sugar. Second is phthalate solution B, which contains potassium sodium titrate or Rochelle salt and sodium hydroxide. It provides an alkaline medium and stabilizes the CO2 plus ion, allowing the reaction to occur efficiently. Next is the sugar sample solution, which contain reducing sugars such as glucose or fructose. This sugar react with phthalate reagent during titration, and their concentration can be determined from the volume of solution used to reach the endpoint. Last but not least, methylene blue. Methylene blue is used as an indicator. It is added near the endpoint. And when the blue color disappears, it indicates that all the CO2 plus ion has been reduced, helping to identify the endpoint accurately and ensure reliable result. Next, I will briefly present the volumetric redox titration using Verheling's method to determine reducing sugar concentration. The procedure consists of 4 key steps. First, we mix equal volume of Franklin solution A and B in a conical flask and bring it to a boil. Second, we gradually add the sugar solution from the burette into the boiling mixture until the initial blue color almost disappears, forming a red precipitate. Third, we add a few drops of methylene blue indicator and continue titrating under heat until the blue color completely vanishes, leaving a distinct brick red precipitate. This marks our precise endpoint. Finally, we record the volume used and calculate the exact concentration of the reducing sugar.
This is the example result of the determination of total sugar content via volumetric titration. We have 3 samples of our result, which is commercial carbonated soda, packaged fruit orange juice, and the commercial isotonic drink. For commercial carbonated soda, we get the average titration volume 12.15 ml and the total sugar content 10.20 gram. The compliant with food regulation are non-compliant because exceed the daily limit. For the orange fruit juice, we get 40.80 for the average titration volume, and then for the total sugar content, we get 11.80 gram. Also, the compliant with the food regulation are non-compliant. And the last one, for the commercial isotonic drink, we get the average titration volume 5.20. For the total content sugar, we get 4.10 gram, and it is compliant. Based on our result, we can interpret that packaged fruit juice contains the highest concentration of total sugar at 11.80 gram per 100 ml. This is because driven by the combination of natural fructose and the added sucrose. For carbonated soda, it is closely followed by 10.20 gram over 100 ml. This is because reflecting the high amounts of the high fructose corn syrup, also known as HFCS. This is used during the manufacturing process. And the last one, for our isotonic sport drink, the result of the record, the lower sugar content 4.10 gram over 100 ml. This is aligned with the standard formulation designed for the rapid fluid replenishment rather than high calorie intake. Based on our application of analytical chemistry in food quality analysis of sugar, we can make a conclusion about our objectives are fully fulfilled because the total sugar concentration of different commercial beverage was successfully determined and quantified through a classic volumetric redox titration method. And the second one, for public health insight, the experimental value proved that both packaged fruit juice and carbonated soda carry a high sugar load that easily exceeds the standard daily nutritional recommendation. And the last one, for the food quality value, this screen confirmed that simple, cost-effective chemical titration remain vital and highly reliable tools for routine food quality analysis and nutritional labeling compliance in the